So I'm going to be talking about Deligne cohomology, but I'll be maybe doing it from the perspective of valence, but I'm not talking about valence and Deligne cohomology. There's something else that's related. I'm not going to tell you what that is, but just so you don't get confused. Deligne cohomology a la Valenson is not Valenson Deligne cohomology. Just wanted to get that out of the way. Okay, so but what is Deligne cohomology? It's a cohomology theory for complex manifolds. Which refines the usual singular or sheaf cohomology, integer coefficients, by including some differential formula. It makes sense that there should exist some refinement because this only uses the topological space M, but we have more. We have a complex manifold. We should be able to make some refined cohomology theory. Let me give some motivation, some motivation for the definition. But let's say what kind of thing is Deligne cohomology going to be good for? Let's say we have a holomorphic vector bundle over a complex manifold. So this is simply the natural notion of vector bundle once we're doing complex geometry. So it's the thing that corresponds to locally free modules over the structure sheaf of holomorphic functions. Then, well, certainly we get a topological vector bundle, complex topological vector bundle in the topological space. And then you have, as is normal in algebraic topology, you have a theory of Turing classes, which lives in H2P and coefficient in Z. And what we want to do is we want some refined coefficients denoted Z weight P sub D for Deligne, which map to Z, and such that in the presence, when you have this holomorphic structure on your topological vector bundle, this usual Turing class in here functorially lifts to this weight P degree 2P Deligne cohomology. Now, before I go on and explain in more detail what this refined coefficient system is here, I want to draw your attention to a phenomenon, which is that now I've got a P also in the coefficients and not just in the degree when I'm talking about the Pth Turing class. And if you're only familiar with the topological story, this might seem a little strange at first, but I want to claim, the first thing I want to claim is that secretly the same thing is happening in the topological story as well, that it's kind of a little bit of a lie when we say that Turing classes take values in cohomology with Z coefficients. So remark why coefficients depend on P. So in fact, if you trace through very carefully what's going on with Turing classes for topological vector bundles, you'll find that, for example, the first Turing class of a line bundle, well, it's supposed to be living in H2 of M with coefficients in Z, but not really. What is this Z really that serves as the coefficient system for the first Turing class of a line bundle? This Z, if you trace things around, it's actually the integral H1 of non-zero complex numbers. And that is a free abelian group of rank 1, but it does not have a canonical generator. So there's a canonical expression for this, which is you can write it as the following free abelian group of rank 1. It's this abelian subgroup of the complex numbers, 2 pi I times C. So if you want to be serious about doing even the topological Turing characters, when you're doing the first Turing class, when T equals 1, it's really not supposed to be with coefficients in Z, it's supposed to be with coefficients in 2 pi I Z. And if you trace through for the higher Chern classes, for example, thinking of the splitting principle or something like this, then you'll find that this coefficient system is actually supposed to be the p tensor power of this free abelian group of rank 1, which can be written as 2 pi I to the p times e. So in fact, there's a hidden dependence on p. And this is actually a good way to know, for example, this is a good way to remember, for example, how complex conjugation is acting on everything, in which behavior of Chern classes of a real vector function and so on, is to always think of it like this. So the fact that these refined coefficients depend on p should not be a surprise, because the original ones actually do too. We just suppress that in general. Any questions?
When you say factorial, you mean the power?
I mean, for pullback of vector bundles.
Oh.
Yeah. So this will be a contravariant cohomology theory. When you pull back a vector bundle, the characteristic classes will be pulled back. I don't mean that a map of vector bundles induces a map of classes. That statement doesn't make sense, and it's not what I mean. Yeah, thank you. Okay, so that was a small remark. But now, how to motivate the? I haven't said the definition. How to describe the definition and why it is what it is. So let's look at to define ZPD. Let's look at first term passes again. So classically, again, in topology, if you take the first term pass of a vector bundle, it's actually the same thing as the first term pass of a line bundle, that line bundle being the top exterior power of that vector bundle. So the theory of first term passes actually reduces to the case of line bundles. That's my notation for the top exterior power of B. So the refined theory of first term classes that I'm talking about will also have this feature that this equation will be true. So in other words, we really only need to understand first term classes of line bundles and how to refine them. Well, there's a tautological refinement. So let me recall a description of this. So one description is of the first term class. You can, a line bundle on a complex manifold, the isomorphism classes of line bundles are classified by this H1 group. This is the sheaf of invertible holomorphic functions on your complex manifold. That being because this is just what transition functions between line bundles are. They're invertible holomorphic functions. This guy, we want to this is a multiplicative abelian group, but we want to linearize it to something additive, so it's natural to look at the exponential sequence, which is actually a short exact sequence of abelian groups. And here's where our 2 pi I z comes in fact, as the kernel of the exponential. And then we simply take the boundary map in sheaf cohomology for this short exact sequence of sheaves. And that defines the first term class. So, this suggests an extremely tautological way of refining the first term class of a vector bundle to a more refined coefficient system. So this suggests setting ZP1 to be equal to O cross, but to get the degrees to work out, we should have this O cross not be sitting as a sheaf in degree 0, but it would be sitting as a sheaf in degree -1. Z1, thank you. Ah. Yeah, it should be O cross sitting in degree -1, so that H1 of M with coefficients in O cross is the same thing as the H2 of M with coefficients in this complex of sheaves here. Okay, so that works. Then we can define a first term class for vector bundles with values in this, but it doesn't. But to generalize this to hierarchy, we should look at it from a different perspective. So let's reinterpret this. So we have O cross shifted by -1. And then the thing that gave us the topological term class was the boundary map here in the exponential sequence, which goes to 2 pi I z. Now sitting in degree 0. And what we can do is, we can look at de Rham cohomology data. So we can make another complex of sheaves, which is the holomorphic de Rham complex. This book. And then we can note that if you're a class which comes from here, then you actually have a refinement, which is that you can put a 0 in the first spot. So here we're in degree 0, here we're in degree -1, etc. And this refinement here comes from the d log map, the logarithmic derivative map. So f goes to df over f. Which is equal to d of log of f when log of f exists, which it does locally. So this map, these are all complexes of sheaves. Yeah. So this map is just the inclusion of these constant functions into all holomorphic functions.
That's maps of chain complexes.
Mm-hmm. And this one's living in degree -1. This cochain complex starts in degree -1, and this comes from the homomorphism of abelian group sheaves from O cross to omega 1, which sends f to d log f. Sure. And we have a commutative diagram like this, and it's actually a homotopy pullback. So the reason being, basically, what's the difference? It's the same thing as saying the difference horizontally is the same as this difference horizontally. This difference horizontally here is just functions sitting in degree 0. That's, difference will exist here. But the difference here is also just functions. Oh, sorry, functions sitting in degree -1. If we're over there, it would be degree 0, then it shifts over here. But the difference here is also functions sitting in degree -1 because of the exponential sequence. So, okay. So another way of looking at this tautological refinement of the first Chern class is that it's a statement about what happens to the tautological first Chern class when you try to represent it as a de Rham cohomology class. It's the statement that it can be described only using differential 1 forms and 2 forms and beyond. You don't need to talk about functions. And it's basically because of the existence of this. So in other words, this is saying that for the first Chern class of a line bundle in de Rham cohomology can be written in terms of a check cocycle with coefficients in omega 1. So you can start at omega 1, you don't need omega 0. Okay. Questions about that? Okay. So now that we, oh yes. No? Sorry, let me be more precise about what I mean. On the bottom, I mean, what's the difference between these two things? Or in other words, what's the homotopy fiber of this map? And or let's look at the homotopy cofiber. Because then the difference is just, the homotopy cofiber is just going to be omega 0, which is functions. Okay? Whereas the homotopy cofiber here, by that short exact sequence, is just functions. Yeah, so and you can check that those two match up, and that makes this a homotopy cofiber. Okay. Okay, so then this suggests the definition. Again, this is Bailenson's perspective on the being cohomology. Right, so for P and Z, and maybe you shouldn't think about the negative ones, but the definition makes sense for all P. Define DPT so that it fits in a homotopy fallback of complexes. So here we have 2 pi algebra PZ. That's the singular cohomology part. And then that always maps to the de Rham complex in the exact same way as before. And then here we put the p term of the de Rham complex. So this is in degree -p. So that this just comes from the inclusion of complexes. So we're defining it to fit in a homotopy pullback square like this. Okay?
Sorry, can you once again, like you said, some interpretation?
Yes.
Is it interpretation of this pullback, like how we, what's your interpretation?
So a reinterpretation of this complex O cross shifted to degree -1 is that it is the homotopy pullback of this diagram here.
Did you say something like how we think about, like, morally, how this picture?
Oh, I said that it says that if you have a line bundle, a complex or a complex vector bundle, its first Turing class, if you move it into Deligne cohomology via the comparison with Deligne cohomology, then it admits a representative which can be described purely in terms of a check cocycle of the coefficients in omega 1. So you don't really need the image of D you don't really need the D map from omega 0 to omega 1.
And so they're on the bottom you restrict further.
I'm sorry?
On the bottom you restrict further.
Yes, that's right. You restrict even further. So the claim is that the peak Turing class of a vector bundle on a complex manifold will always have a Deligne representative where you don't need to know about 0 forms of the P-1 forms to write it down.
Okay.
So it's difficult. You guys using all of them.
Sorry? That's the only convention that exists in my world. Thank you for giving me the chance to okay. But in fact, yeah, exactly. When I say this is in degree -p, I mean homological. Other questions? Please keep the questions coming. I think they're doing a lot to help clarify what
By the
I'm
way,
trying to say.
can you repeat the
Yes.
questions?
Oh, I'm sorry.
No,
Yes,
no
I
worries,
can,
can you-
I can, yes. Robert?
He appears twice in that pullback square.
This, yeah.
Yeah, or independently. Can you explain why the two P's need to be the same?
They don't. The question was, why do these two keys need to be the same? The answer is they don't. But they are the same. They are the same. Okay. So in fact, for some purposes, you want to have different P's. If you're talking about vector bundles with connection, you want this to be P and this to be 2P. Okay. All right. Other questions? The more questions you ask, the less material I have to present later. All right. So yeah. All right. So now what's the point? That's perfect.
Exactly.
Okay. How many is this? Oh, yes.
So, apart from like being correct in terms of units, those these 2 pi I to the P to the level play any role in developing like simple. Like what is the difference between that and when you put C instead?
Well, this is correct, and it's not correct. It's easy.
Unless it just is a morphic.
Well, then you'd have to put a 2 pi I to the P in this map. Or divided by, or 2 pi I to the minus P. And then that's bad. That's not, I mean, that, you could do that, it's the isomorphic, but I prefer the maps to be natural. And I don't have to write down what the maps are.
It also tells you how complex conjugation acts, right?
Yeah, that was my point that I was making earlier, yeah. Oh, I forgot that. The question was, never mind. No. Okay, so here are some examples of these Deligne complexes. Okay, well, this is just the constant sheaf Z, and as I already said before, Z1D, this is O cross -1, and this implies that there's a tautological first Turing class of line bundles in H2 M coefficients. Okay? But also, and this is an important point for constructing higher Turing classes, this is a graded commutative ring. That's one of the nice things about writing this as a homotopy pullback. So These guys form a graded commutative ring, just obviously, by multiplying them. De Rham cohomology is multiplication. And this filtration is multiplicative. So if you're in the filtered, this is called the filtered piece of it. The notation for this is FP omega de Rham, the filtered piece of the de Rham cohomology, de Rham complex. And if you're in filtered piece P and something in filtered piece Q, you multiply them together, you're in filtered piece P plus Q. It's just obvious. And then the homotopy pullbacks, the rings work nicely with respect to homotopy pullbacks, so you get some product structure on Deligne cohomology, even before taking cohomology, but then also after you take cohomology. Of course, you also have to remember that the cohomological degrees are also going to add. So there's a ring structure in Deligne cohomology as long as you remember all the weights. Okay, so I'm just the most basic. I'm just saying there's okay. All right, there's pullback functoriality. Constant sheaves, obviously, there's a pullback comparison map. The differential forms also, there's a map from the pullback. If you have a map from M to N, there's a map from P forms on N to P forms on M. And so that's like ring cohomology N, ZP. Again, it comes from something just on the sheaf level. Pullback functoriality. And then the next, or the last most important basic property of Deligne cohomology is the projective bundle formula. So if B is a vector bundle, holomorphic as always, then we can make the projective bundle, this corresponding projective bundle, and then you can ask how to determine the Deligne cohomology of this guy in terms of the Deligne cohomology of that guy, and the result is that Deligne cohomology, I don't know, there's two stars, but this is graded free of rank D. Let's say it's D-dimensional. Graded free of rank D over the analogous thing on the base. Classes, one unit in the ring for the ring structure, the first Turing class of the tautological bundle, all the way up to the D minus first Turing class of the tautological bundle. Where those are these tautological first Turing classes and weight one Deligne cohomology that I was talking about.
Why did you put 2 stars?
Just to remind you that there's that there's two independent indexes.
Okay.
Yeah.
Okay.
So that's probably very bad. And then maybe just to make it unambiguous what I'm talking about.
And this is true before global. Is this true before global sections, like with the push forward?
What did you see?
The question was whether this holds before taking global sections, like if you make some, because both of these are the cohomology of something on M, like you can push forward. It sounds like it should be true, but I don't want to. Yeah, that's a good question.
This is some kind of Larry-Hirsch kind of argument, right? That you say that.
Well, you have to be a bit careful here. I think it's true, Maxime. Yeah. But you have to be a bit careful with Larry-Hirsch. There are infinite dimensional spaces floating around. So, but yeah, I think it's true. Okay. Okay. So why am I mentioning specifically these properties? Well, they're fundamental, but I mean, Grothendieck explained how just having these properties already gives you a theory of Turing classes of vector bundles, which is what I started motivation So according to Grothendieck, there's this nice trick. Once you have the projective bundle formula, you can expand. You can take the first Turing class of the topological bundle in the projective space and now raise it to the dth power, and then in terms of previous powers. And then the coefficients define the Turing classes. And you can check that the degrees and the weights and everything. By the way, this is called weight, and the cohomological degree is called degree. And the degrees and the weights conspire to make it so that this does live in the expected degree. And it is a refinement of usual topological Turing classes via the comparison. And it has the same formal properties as usual Turing classes. So functorial under pullback, you have a Cartan formula. First Turing class is the first Turing class of the top exterior power, and so on. Okay. Other questions? Yeah.
Is this also something you can get via splitting principle?
Yeah, you can, but it's more complicated to try to do things that way because calculating the cohomology of BGLN is more complicated in this setting, but you can do it. It turns out you can do it. I'll maybe discuss some things like that later.
You can also do more generative principle one.
Yeah, that's right.
Where does the homomorphicity of the deductive bundle come?
Oh, if I want to build a projective bundle that's a complex manifold, then I need, so the question was, where does holomorphicity of the vector bundle come in this construction? And it comes in because I needed to be able to take the Deligne cohomology of this object. So it needs to be a complex manifold. Okay. All right. So let's do some more examples. By the way, I will explain to you, I was giving this motivation like Turing class is great. I will explain to you more specific motivations for all of this. Like why do we care about having these refined Turing classes and so on. But right now I just want to get through some more properties and examples of Deligne cohomology. So let's see. Here's some examples. Oh, okay, so if p is less than or equal to 0, then ZPP is just 2 pi I p to the 2 pi I z. So in this range of non-positive weights, this is sort of purely topological. It's the same as the purely topological story. But also, if p is strictly bigger than the dimension, the complex dimension of your manifold, then it's also in some sense purely topological, but in a different way. So then this is C modulo 2 pi I dz, shifted down in degrees by 1. So the reason for that is, I shouldn't have ever erased the definition, but now you get to use your powers of imagination. Draw the diagram defining the Deligne complex in your head. Are you done? Okay. Now, let's think about when p is bigger than the complex dimension. Then there are no p-forms or higher on your manifold, right? So the whole lower left corner of your diagram in your head is equal to 0. Okay? So that the Deligne cohomology in that range is just the homotopy fiber of constant coefficients 2 pi I p z mapping to de Rham cohomology, de Rham complex. Now the holomorphic Poincare lemma says that de Rham complex is resolving the constant sheaf C. So that's the same as cohomology with C coefficients there. And then the long exact sequence in cohomology is basically giving you this here. Did that work? Okay, I'm seeing enough nods. People are very polite. Okay, so there's these two ranges where you have something purely topological, but But the coefficients and the shifts are different. And then in between, you've got all these differential forms contributing. So it's not purely topological. Okay. I was going to make a comment about Stein spaces. Well, let me just make a remark that, let's say if M is Stein. So one equivalent characterization of that is that it's a closed submanifold of some C to the N. It's kind of opposite end of the spectrum from compact and proper. Then all these sheaves omega I are acyclic, so there's no higher cohomology. And then in particular, this implies that that if you look at, say, if you look at HP of this P-filtered piece of the Deligne cohomology, Deligne complex, then this is just the closed P-forms, holomorphic closed P-forms. And this is a huge vector space. It's an infinite dimensional, some Frechet space for the complex numbers. So in general, this cohomology theory is going to, and that, this appears in some long exact sequence describing Deligne cohomology in degree P, weight P. So in general, when you're in the middle here, you're going to get some really big infinite dimensional complex vector spaces as values, occurring as values in your Deligne cohomology groups. So in other words, it's not entirely clear which category you want to think of these Deligne cohomology groups as living in, because it's got some free abelian groups sitting in there coming from the topological part. It's got some finite dimensional C vector spaces sitting in there, but it's also got some infinite dimensional Frechet spaces sitting in there. Okay. But there's something next that happens when you have a compact manifold. M compact, and the total cohomology of, in total period of all these possible vector bundles is finite dimensional. So that the Deligne cohomology groups are always built out of Z's and C's by extensions and quotients. If you think about the Deligne cohomology, when all the cohomology groups of these guys are compact, then it implies the same for all these filtered pieces of the Deligne cohomology, because they're just built out of at most P copies of what you're seeing here. So on the bottom of your diagram, you're only going to see finite dimensional complex vector spaces, and then at the top, because you're a compact manifold, finite CW complex, you're only going to see finite and many Z's contributing to something or another. So in this case, it's kind of finite dimensional, but it's not clear, again, finite dimensional over what. There's some C's and some Z's mixing together, but okay. It's basically finite dimensional in this case. Okay, something even nicer happens when you're not just compact, but you're compact Kähler. So e.g. could be a complexity, could come from a smooth projective variety. So for example, a projective space or any closed submanifold of projective space. Then, in all degrees, the map of cohomology from this P-filtered piece of the Deligne cohomology to the Deligne cohomology that occurs in the bottom of the defining diagram for Deligne cohomology, and this is just the cohomology of the C coefficients. This is indefinite.
Sorry, is it FP?
Probably. Yep, thanks. And then, so the image is what's known as the filtered piece of the wrong cohomology for a manifold. This is the Hodge filtration. And what does this tell you about Deligne cohomology? It means you have a short exact sequence. So, okay, so yeah, we have this pullback defining Deligne cohomology, right? And I just told you in any degree, the bottom map is inducing an injection in cohomology when you have a compact Taylor manifold. The right-hand map, that's from integral cohomology to complex cohomology, that's basically also an injection, except there could be torsion in the cohomology. Just to not worry about the damn torsion, I'm going to rationalize the Deligne cohomology, so that then that part is also injecting in. So then we're just, then it's really easy to analyze. So this tells you that if you take Hi, M, and then Q, P, Deligne. So that's just, you just rationalize this Deligne cohomology complex. So you have 2 pi IPQ instead of 2 pi IPC. Then this surjects onto the P filtered piece of the Hodge filtration on the complex cohomology, but then it also lands in this rational subspace. So that's a surjection. And then what goes over here is some quotient of a cohomology group in the previous degree. So you look at, again, the topological cohomology with complex coefficients, but in degree I minus 1, and then you have to mod out by the images of the, here it's an intersection, here you mod out by the images. So you take Fp of H I minus 1 MC plus H I minus 1 M 2 pi P minus 1 C or Q. Okay? So you get a short exact sequence like this. Now this is all taking place inside a rational cohomology group, you could say. So it's those rational cohomology classes which satisfy the condition that when you map them to C, they live in the peak stage of the Hodge filtration. But this is all discrete data. This is discrete. Whereas this over here is continuous. You're taking some C vector space and then modding up by basically, well, another C vector space. That gives you a C vector space again. But then you're modding up by some integer lattice or something like a rational lattice, not really, but close enough. So it's something like a torus. So the Deligne cohomology is kind of a way of saying that, okay, a vector bundle or whatever you might have, if it gives you classes in Deligne cohomology, then you learn two things. First of all, your classic invariants, which are discrete, like usual topological cohomology, they will have to satisfy a certain condition. They'll have to live in the P stage of the Hodge filtration. But more than that, it also gives you something else. If that invariant happens to vanish, well, that doesn't mean your vector bundle is trivial necessarily. And you get refined information, then you get something that lifts to you get some continuous parameters. For, say, a topologically trivial holomorphic vector bundle, you'll see some continuous parameters, which you can measure in terms of this torus that appears here. So in fact, if we look at the original case that I was discussing, which is degree 2p, so when I equals 2p, the left-hand side is rationalization of Griffith's intermediate Jacobian. And so, for example, when p equals 1, it's the usual Jacobian. So you might recall some theory of holomorphic line bundles on, for example, compact Riemann surfaces. There's the topological invariant, which is just degree, which is an integer. But then beyond that, there's continuous invariants, which are the points in the Jacobian. And this picture generalizes that to higher weights, as it's called. So that's okay. Any questions? Okay, so now let me mention some applications of Deligne cohomology. So why do people care about Deligne cohomology? Well, I already mentioned one, which is these intermediate Jacobians. So you get more refined information about your vector bundles by considering their characteristic classes in Deligne cohomology. So even in situations where the usual topological characteristic classes aren't telling you anything, for example, aren't distinguishing two vector bundles, these refined ones often will. And you can also understand something about moduli because these are continuous invariants, not discrete invariants. That's one. Another thing is this theory of secondary characteristic classes of flat bundles. So these are. So the universal case is a fun story. So the BGLNC discrete topology. So you can actually look at, so this Deligne cohomology makes sense not just for complex manifolds, but also for stacks. And you can even do it for this stack, which is B of this discrete group. This discrete group being viewed as just a zero-dimensional complex manifold, infinitely many components, but okay, you can still do it. And then the Deligne cohomology for a point, or a union of points, is purely topological. It's either Z in negative weights, or it's C mod 2 pi I Z shifted down by 1 in positive weights. But there's no differential forms on a point or on a zero-dimensional manifold. And if you think about what it gives you, you actually recover, in this universal case, you recover these so-called secondary characteristic classes with these coefficients, which, when you map under the boundary, you get the usual term classes, the usual topological term classes. So you recover, for example, recover a new proof of the fact that the topological Chern classes of a bundle with flat connection or a local system are always rationally trivial. They're zero when you tensor with C, because boundary map and then change coefficients zero for trivial reasons. But you actually get something more, you get a refinement of that fact to a secondary characteristic class of these torsion coefficients. And these are known as Chern-Simons invariants. And in low-dimensional topology, they're actually extremely important. So if you start with a hyperbolic 3 manifold and the canonical representation of the fundamental group, then you can get an invariant which remembers both the volume of the manifold and also something more refined, some angular coordinate.
Just making sure this quickly line is a 0, P strictly bigger than 0?
P bigger than, yeah, strictly bigger than 0.
Here, discrete means like some space embedded as a discrete stack, or because BGLNC is abstract group.
Yes, abstract group, yeah. So for example, GLNC discrete is an abstract set. I can do it as a complex manifold of dimension 0, but as such, it's also a group. I can take B of it.
Yeah, but you said, but that doesn't classify complex topological complex.
No, it classifies flat vector bundles.
Ah.
Vector bundles, local systems, classifies local systems. Yeah, the transition functions would be locally constant functions. Like a continuous map of a discrete set of locally constant. Okay. So that's nice. That just comes that Valenson made this observation that this whole theory of Chern-Simons invariance and flat vector bundles just comes immediately out of the formalism of Chern classes and size and Deligne cohomology. Yes. Question? Hello. Yes. No, I'm not saying anything about Chern-Simons invariance of non-flat bundles. Yeah. Thank you. So if you're trying to quantize something, then I can't let them. Okay. Right, but maybe the most important, or I don't know, the most compelling for me at least, application of Deligne cohomology is in arithmetic. So this is this philosophy of Arithmetic, or one interpretation. So let's say, for example, we start with a regular proper scheme over Z. That's this math cal X. Well, it's regular, which means basically no singularities, and proper means that basically it has compact fibers. So fibers are complete curves over whatever residue field you're or not curves, complete varieties over whatever residue field you're looking at. But that doesn't mean that this guy should be thought of as compact. That is, the total space should not be thought of as compact because the base should not be thought of as compact. So spec Z is, in terms of function field analogy, it's like spec of the affine line, spec of FP bracket T, say. So it's like A1 over FP, and that's not compact. It's not P1. It's missing a point at infinity. So in the Arithmetic philosophy, well, one imagines that spec Z is not compact, and so and then anything also proper over spec Z is also bound to not be compact. You're missing some points at arithmetic infinity. Okay, well, so okay, fine. But what do we do about this? Now we don't have access to the missing point. We don't have access to an analog of P1 over FP and then its point at infinity. But we do have access to something that is like a small neighborhood of the missing point at infinity. Because the small neighborhood of the missing point is just a completion of this ring. It's the FP Laurent series in like inverse coordinate, local field living at infinity. And that we have an analog for, a perfect analog for, and it's the real numbers. So the FP bracket T mapping to this is exactly like Z mapping to R. Okay, fine, again, totally fine. But so what does this tell us? The fact that such a script X is not compact, what does that tell us? It tells us that whenever we consider cohomological invariances such as an X, we shouldn't consider them in isolation. We always have to consider them together with their compactly supported analog. So on X, should consider not just cohomology, but compactly supported cohomology. Whatever that is, where the compact support is again in this arithmetic direction, real numbers. And in the, but to know compactly supported cohomology of A1, you don't actually need to know how to compactify, and you don't need to know the point at infinity. It is enough to know the small neighborhood at infinity, because then you could still define the relative cohomology of A1 with respect to this small neighborhood of infinity, and that is also just like compactly supported cohomology. So this is good news. We actually can define all of the objects needed to talk about compactly supported cohomology of this non-compact thing without having to think about how to compactify it. So this should be, so whatever cohomology theory you imagine, you take maybe some R gamma. So it should be a homotopy fiber of this mapping to R gamma of whatever's sitting near infinity in this Arithmetic picture. And that is, you take the complex points of such an X, which is a complex manifold, but it should be really over R instead. So maybe we formally mod out by complex conjugation. Yeah. And then we take the homotopy fiber of something like this.
Sorry, why mod out and not fixed points?
Because then if you take cohomology, it's going to turn into a fixed points. That's one answer. And then the again further development of our idea is that if cohomology means motivic cohomology, then this should be Deligne cohomology. this Valenson again. I think probably everything I'm saying is Valenson, even if I say it's Deligne or Arithmetic. That's, sorry?
What is this?
Well, the thing the arrow is pointing to, yeah, sorry. Then this part here, without the C2. Yeah. So then there's always going to be a complex conjugation action. If you're, there's always going to be a complex conjugation action on the Deligne cohomology in this situation. Okay. So, and why do I say, why should this be Deligne cohomology? Because when you look at things like special value conjectures for L functions or zeta functions or what have you, then that's what plays that's what's playing the correct role in everything. So let me do the most basic example. What time? I'm very confused about the clock.
The clock doesn't, the format that doesn't work. You have 10 minutes
I
approximately.
have 10 minutes left? Okay. So, an example would be if you look at some, you can look at motivic cohomology of spec Z. The most basic example is spec Z itself. And then this also comes with weights, and when we rationalize, HI, QP, this always will map to Deligne cohomology of a point as a complex manifold of QP Deligne coefficients. And then we can take the C2 fixed points, but it doesn't matter, we're rational. So this, it turns out, so let's say in weights p bigger than 1, then this is non-zero if and only if I equals 1 and p is odd, and then it's one-dimensional over Q. This is all Borel, by the way. Everything I'm about to say is Borel, as reinterpreted by Valenson. So that the only non-zero values are when I equals 1 and p is odd, and it's the same thing here. So same here. If you just look at the calculation that I gave for what the Deligne complexes are, and then it's isomorphic to C mod 2 pi I p Q. But note that this admits a map to R. So P is odd, so this is imaginary. So I can just take the real part.
So P should be.
Oh, thank you. Yes. Thank you, sir.
No. I mean, power of 2 pi doesn't have to be odd. It's like P minus 1 divided by 2 or something like that. You have P odd.
Yeah.
Here you have like if P square minus 1, I think it should be 2 pi more than.
I maintain that this is correct.
You get only odd power.
I passed to the C2 fixed point.
Okay. Yeah, sorry.
Yeah.
Yeah,
Okay. Right. So then we have this one-dimensional rational vector space. So this is where this is non-zero is exactly matching up with where this is non-zero. But then we get something. We have a one-dimensional complex rational vector space, maybe no preferred generator, well, mapping to R. The other thing proved by Borel is that the image of this one-dimensional rational vector space can be described. There's maybe some power of pi, and then you have the odd zeta value, zeta p, times the natural Q structure on this, which is just Q sitting inside R. This is a Riemann zeta function. Okay. So this somehow this so-called regulator map. I don't know. Well, see, zeta values are popping up. By the way, if you take p equals 1, this side is non-zero more often than this side, and that corresponds to the pole of the Riemann zeta function at s equals 1. So there's really a very tight analogy between what's happening for Deligne cohomology and what's happening with the Riemann zeta function, and that's just the simplest case of this kind of fascinating story with Valenson's conjectures.
So,
yes?
is this an example of something, or is it just an example of what this map looks like?
It's an example of what this map looks like. It's hinting at Valenson's special value conjectures, which are about special values of L functions, and they're exactly about the relation of the behavior of this regulator map. So that's what's suggesting that the thing playing the role of motivic cohomology for the part at infinity should be Deligne cohomology of a complex manifold, together with some C2 action.
Sorry, quick question. So, I mean, for major wiles, we're supposed to think of the zeta function as being related to like the characteristic equation of like a law action on the tape twist of a top cohomology. Is there some similar thing if we replace like tape twist of the top cohomology with instead this refined Deligne?
Well, that's a different regulator you can look at.
Different regulator.
Yeah. I mean, it's a p-adic L function to a p-adic regulator.
Right.
Yeah, so this is the, if you're interested in the usual complex L function, this regulator. Okay. So, where am I? So now I have maybe 5 minutes, is that right?
Yes.
Okay, perfect. I'm going to tell you what the goals of this lecture series are going to be. After the introduction to Deligne cohomology. So I want to try to make precise the idea that Deligne cohomology is the analog of motivic cohomology for complex manifolds. So motivic cohomology is some kind of universal cohomology theory, and I wanted to try to express a sense in which Deligne cohomology is also a universal cohomology theory. So it's not by definition. Definition, you just stick in these differential forms, and that's your definition. But the other thing is related to the Hodge conjecture. Now, please do not think that I'm trying to prove the Hodge conjecture. Nothing could be further from my mind. But I just want to understand basically what the statement is saying. Okay, so the Hodge conjecture, one way of formulating the Hodge conjecture is that if you take, you can take the K0, we're supposed to be talking about K theory, right? The K0 group of vector bundles and rationalize it, and there's a Chern character map now to the direct sum of all these Deligne cohomology groups, degree 2p with weight p. And the Hodge conjecture is exactly stating that this is surjective. Oh no, sorry. This goes further to direct sum over p of this. Remember the discrete quotient I had of this? You have rational cohomology classes which lie in the p stage of the Hodge filtration. That's called the Hodge. When I was talking about the Griffiths intermediate Jacobian, I should have also mentioned that the discrete thing has a name too. It's called the Hodge classes, the weight p Hodge classes. Rationalized maybe. And the Hodge conjecture says that not this map, but this composite is surjective. So for any possible discrete cohomology class satisfying the appropriate Hodge theoretic conditions, there should be some linear combination of vector bundles that's realizing it. And this is for M smooth projective. Something algebraic. Not Taylor, really smooth projective. And this is a funny statement, because it's known that this map here is not surjective, let alone an isomorphism. And if you try to perturb this by going to like K1, and then you have Deligne cohomology in the next, or the degree down for Deligne cohomology, then it's just blatantly false, no injectivity, no surjectivity. So it's an extremely delicate statement, this Hodge conjecture. It's a surjectivity here, but some of the natural lift is not lift. Something we're finding, this is not surjective, there's no isomorphism claims. That's what makes it so hard to prove, is that it's very delicate. You perturb it a little bit, you just get a false statement. But this is not the way the world should be. So we want to modify this K0 vector bundles on M using continuous K theory. To get a theory where it's reasonable to conjecture that K0, to be some version of nuclear with M. It's actually isomorphic to this relevant Deligne cohomology. And then so you can make a refined statement, be true in every degree. Right? And then I also want to make Riemann, I didn't really mention Riemann-Roch, but I want to make Riemann-Roch more transparent. So I didn't mention this Arithmetic, Riemann-Roch, and things like this, but it's, again, refinements of usual Riemann-Roch, which is a statement about cohomology, usual cohomology, then you can refine it to something in Deligne cohomology. And it's actually not even known in full generality in that context, but so there's definitely something to understand there, but the things that I'll talk about, it's pretty clear how to prove it in full generality. So when you understand things like Riemann-Roch values in Deligne cohomology, which is closely related to Arithmetic Riemann-Roch, I want to make that a lot more transparent than what it currently is in the literature. Okay. Because I had restricted to degree 0 there. But of course, there should be I'll discuss a statement about what this should be in all degrees and without the rationalization. Okay, that's it for the first lecture. Thanks for your attention.